And hello everyone, thanks for joining us, for your time as well. So today what I'm going to present is some of the latest developments from the Evosep team, specifically focusing on workflows for plasma profiling that are completely integrated with the Evosep 1 system. So I think Boris already highlighted very nicely the relevance of plasma and serum for clinical diagnostics, clinical proteomics. It's a biomarker that's easy to obtain, and it contains a lot of secreted, tissue secreted, cell secreted biomolecules, including proteins, which, if we can measure sensitively, robustly enough, can be used as a proxy of a patient health status. And he also mentioned some of the challenges that come with doing plasma or blood proteomics, serum or plasma proteomics. We all know about the challenge of dynamic range. There's estimated 10,000 proteins in plasma, but we can measure only less than 1% of those because most of them get hidden by the high abundant proteins that cover 95% of the protein abundance. But beyond that, our method needs to be also robust. They need to be scalable in terms of the number of samples we can process, and also need to be scalable in terms of cost when you start processing these larger cohorts. And lastly, I think they need to be standardized and also be easy to implement across different sites and different laboratories. And this is what we're trying to achieve when we're trying to develop these end-to-end workflows that are enabled by the Evosep 1. So our story is basically centered around a really key characteristics of Evosep 1. That's the Evotip. It has numerous advantages. It's fully integrated with the LCMS system. It has numerous advantages, and I just want to highlight some of those that are most relevant to specifically for plasma profiling. First and foremost, we're able to directly elute the samples into the analytical column without needing to do additional steps such as elution, drying, and so on. And this has a big effect when it comes to trying to fish out these low abundance proteins from plasma. Here on the right, you can see the number of precursors identified across the chromatographic gradient. This was a plasma sample processed with the magnet protocol, which I'm going to describe a little bit later on. And you can see that across the gradient, we consistently identify more precursors with a direct Evotip-based analysis. And this translates to approximately 10% more proteins quantified, identified in this particular run. Another really important feature of the Evotip is that it really is a fail-safe device that protects your analytical column, it protects your mass spec, which is really important when you start to push this large number of samples that can contaminate the system. So this is done because of two things. One is because we can do partial elution, so if we elute peptides with no more than 35% signature, which means that a lot of the contaminants remain on the Evotip. And it's a single-use device, so we can discard each Evotip with each sample. So if you have a problem with a specific sample, this doesn't affect the rest of your batch, it doesn't affect your more expensive component of the LCMS system. And you can see this here where we analyzed over 400 injections with no considerable difference in back pressure indicated, and also no considerable difference in changing the retention time for these targeted peptides we are looking at. Another important feature with Evotip is that it allows us to handle very diverse type of samples. So here we analyzed 5 boxes of plasma samples, as well as 5 boxes of helidigest. These are very diverse in terms of the complexity, in terms of the dynamic range, in terms of the type of contaminants they carry. But with both set of sample inputs, we can get very reproducible analysis. And this is important because it enables us to then couple the Evosep and the Evotip to pretty much any type of sample source or sample preparation technique And this then opens the door for us for applications development to start doing this modular sample preparation end-to-end solution, which I'm going to be describing now. And of course, the last feature is the automated loading. I think there's different ways to this. Boris already mentioned one where you can do it in a more complex liquid handling system with integrated centrifugation systems. If you don't have such, you can also do this using this much simpler but very efficient positive pressure based loading using a sandwich based approach, where liquid handling will load solvent A, followed by air gap, the sample, and another air gap with more solvent A. And then with a single push, then the whole set of samples are loaded. And this can be done with an 8-channel liquid handling pipette or with a 96-channel, like the one in the Azure and Brown robot. And why this is important is because now we can actually do end-to-end workflows that are completely hands-off without any operator intervention, starting from the raw plasma all the way to peptide-loaded Evotips. So with all this kind of weapons in hand, we are able to now start thinking about how do we add different sample preparation strategies and integrate them, streamline them together with the EVOTIP and the Evosep one. And these strategies of these sample preparations, we see them as individual modules, so that they can be utilized on their own, but also they can be utilized in combination that form different, more complex pipelines, or they can be utilized side by side. So today I'll show you an example where we use the digestion module to do undepleted plasma, and we use the enrichment/depletion module to do more deep plasma profiling. And this is then put on the same deck for the liquid handler, so you can actually run both modules together if necessary from the same sample source. So what strategies do we use? What sample preparation strategies have we adopted? For the neat plasma profiling, we've taken the protein aggregation capture methods, and we've done this because it's universal in terms of being able to handle a wide range of sample sources from tissues, cells, biofluids, including plasma. It's a cost-effective method because you can use any type of magnetic bead, and also it decouples your extraction from your digestion through a on-bead washing step, which means that you can use very harsh conditions for extraction to solubilize your proteins. You can remove those contaminants, and then you can do on-bead digestion without any interference from these contaminants with the enzyme. For the deep plasma profiling, we've adopted the magnet method to automate, and this method allows a deeper look into the plasma profile by effectively compacting the dynamic range. And this is done by enrichment of membrane-associated proteins and as well as depletion of high-abundant plasma proteins. Ultimately, our aim here is to integrate these two workflows into a end-to-end solution, the streamlined with Evosep one that is fully automated, completely hands-off. Both workflows have been miniaturized, so you can use as little material as possible. You can therefore reduce your costs, electrical costs for these assays, and then we standardize to with very user-friendly methods interfaces, which I'm going to touch upon at the end of the presentation. So this is what the deck would look like, what's been automated on an OpenChon system. Especially for the neat plasma profiling, for the undepleted plasma profiling, we use a hydroxyl magnetic bead to do on-bead precipitation. We start off with a solubilization step with high percentage of detergent that also allows to do single-step reduction and alkylation, followed by aggregation of proteins on bead using a high percentage of organic, a wash step, a short digestion, and then automated EVOTIP loading. For the deep plasma profiling, we have the same back-end pipeline as for the deep plasma, but we've also added the additional capture and wash step that allows us to capture membrane-bound vesicles and reduce the concentration of high-abundant plasma proteins, which effectively compacts the dynamic range and allows us to go deeper in the plasma proteome. And for this, we use a quaternary ammonium hyperporous magnetic particle. And this is what the deck looks like. essentially we have two magnetic modules. So then we can use that can handle a 96 watt plate. And then we can do the neat plasma and the magnet protocol for deep plasma profiling side by side with 96 samples done in parallel from raw plasma to Evotip loaded ready for analysis without any operating intervention. Alternatively, if you decide you can run either one of those workflows, and this will give you a throughput of 192 samples for this workflow. We use a very low amount of plasma, so volume of plasma, a total of 5 microliters to do both workflows, 1 microliter for the undepleted workflow, and down to 4 microliters for the magnets or deep plasma profiling workflow. And here, the important thing is that we can also scale this plasma inputs up to 80 microliters, and you can match this to your specific plasma preparation protocols, so you can get the best depth of coverage. The experiment we designed to kind of test this setup is to have 2 different plates for each of the workflows, neat and magnet, so that we can evaluate the 2 different positions, which is basically magnetic module 1 and magnetic module 2 to see if there's any bias. And we also introduced some Hila digests, which are used as system stability controls, in other words, controls to measure the variability of the LCMS setup. And then we can separate and measure or estimate the variability of the sample prep versus the variability of the LCMS. So what does the data look like? We see very robust and reproducible protocol. If you look, if you pay attention on the right, this is the precursor level Pearson correlations for the magnets, and for the neat plasma protocol, very high correlation. On top, we see the samples, whether they're coming from position 1 or position 2, and we don't observe any apparent and any apparent clustering, so it's good. So it means that there's no bias across the 2 plates. On the right, we have the coefficients of variance on the protein level. First, we have the Hila data, and this essentially reports on the LCMS variance. So this includes the mass spec, the Evosep one, as well as the Evotip loading. And you can see that this is very low, so we get 3% median CVs from this. The neat and the magnet plasma CVs 10 and 11.5%, and this basically reports on the variability all the way from raw plasma to the acquired data, including the mass spec variability. So if we subtract the variability from the LCMS, we see that our variability for sample prep is in the region of 7 to 8% for the neat and magnet workflows. Next, we looked at how reproducible is this workflow across different laboratories. And for this, we prepared a set of samples using the magnet automated workflow. These samples were prepared on separate occasions, approximately 3 months apart. And then they were sent to 2 different labs, one in the USA, one in Europe. And they were analyzed using different operators on the same Evosep orbital astral system. What we can see, as expected, is that it's a very high Pearson correlation for the precursors when it's within the same lab. Slightly lower Pearson correlation across the labs, but still very, very high, considering this samples processed 3 months apart across 2 different labs and 2 different operators. The same number of proteins identified, and 81% of the proteins that were identified were the same across the 2 labs. Another thing we looked into is do we detect any clinically relevant proteins in our data? So for this, we looked at 2 sources of information. The first one was the list of FDA-approved biomarkers that's reported by RESYN, and the second one was a list of 83 proteins associated with 12 different cancer types as reported in the Protein Atlas, Human Protein Disease Atlas. What we observed is that both for neat and the deep plasma profiling workflows, we can detect approximately 60% of the FDA-approved biomarkers, with 70% of those being below 20% CV. And where we see some benefits going with the deeper profiling workflow is that we can detect really low abundance proteins associated with cancer types down to the range of picograms per mole. And what's good to see is that even though they're very low abundance, we can still detect them at high precision, below 20% CVs. The last thing to highlight is the interface of how you set up these methods. You don't have to be a guru into Python scripting. You essentially would have an HTML-based form that will allow you to interface with the OpenTrons robot. This is still something that's under development, but I don't think it will change a lot from what you're seeing here. So on the left is the form for the deep plasma profiling, on the right is for the deep plasma profiling workflow. And they're essentially the same. The operator will put in the number of samples analyzed, how much to load an EVOTIP, and this will depend on the type of method we're using, the type of mass spec you're connected to. And on the magnet workflow, you also have the option to scale the amount of plasma that you have from 4 to 80 microliters, so you can match your plasma preparation to get the best performance out of the methods. But really user-friendly, really standardized, so you can then be reproducible across laboratories, hopefully help with the implementation of these methods. So just to summarize, I've briefly shown you some of the end-to-end workflows we have for plasma proteome profiling that's being completely integrated with EVOTIP loading and therefore the Evosep 1. They're reproducible across plates, but also across laboratories. They're scalable. We have a throughput of 96 samples if you're doing both workflows on the same deck, or 192 samples if you're doing each of the workflows individually. We've reduced analytical costs as much as possible by reducing the amount of material that you need to do and how much reagents are utilized. And we can detect really low abundant proteins that have clinical relevance, which I think is really important, beside the very deep coverage that you see. And we're also developing these user-friendly standardized method interfaces that hopefully help you to implement these methods in your laboratory. And so with this, I'm just going to end and thank the team from Evosep, as well as Thermo for some of the development work, and the guys in my cost lab for development on the magnet methods. And thank you for your time.